So let's take a look and see what happens when we talk about optical resolution. Now we're going to actually look at the example of the eye. So what happens when we see stuff coming up? Well, most of us have been to an optometrist and have been required to look at the eye chart. And we see the big letter E, and it goes down from there, and the letters get smaller and smaller and smaller. And they say that, the vision that you want to have is 20/20. So at 20 feet, where they place this chart, at 20 feet, in a certain level of light, you should be able to see this row. And this means that for a normal person with perfect vision, 20 feet means that the picture looks like it's at 20 feet. If you go to something that's 20/25, for, say, myself, which I have 20/20 vision, if someone who has 20/25 vision looks at this line, they will see what I see at 20/20 vision. So it's kind of a cool little thing. But at some point, we're going to get to a point where it doesn't matter how good our revision is. The smaller the letters are, the harder they're going to be to see. And we'll see that there's certain letters that show up a lot. E, the first letter we see, the next one F, and actually even P. All of them have this middle line here, this top line here. The P closes it, so an F and a P are just the same thing but closed. The E has the extra little line. So at this point, we can look at these things as, can you tell the difference between these 2 points? Or can you tell the difference between these 2 points? Or an O and a D, can you tell the difference of this little area up here and down here compared to what's happening on an O? So this is what they look for to see when you actually take your eye test. And really it comes down to how much can you resolve. So that concept we were talking about last time in resolution. Well, mainly when we do this test, it's not actually a measure of the absolute resolution of your eye, but more of a resolution of the cornea and the lens, and how your lens and cornea actually focus the light. So even that has some limits on it. It's another type of resolution, but it's not our Rayleigh criteria resolution. So the question is, if we were to look at the Rayleigh criteria, how accurate can we see if we could see at the absolute resolution of our eye? So let's put a couple numbers in on this. If the iris of the eye has a diameter of 5 millimeters, sounds about right, and the wavelength we see is approximately 500 nanometers, kind of nice that we're going to get a 5 and a 5 in here, so we'll see that the absolute resolution of your eye, got to remember that our eye is circular, so we have to use the circular aperture, or the circular opening. So we'll see that the angle that we're able to see is 1.22 times the number 500 nanometers over 5 millimeters, our wavelength over our diameter. And this works out to 1.22, the 5 and the 5 cancel, so we get 1.22 times 10 to the minus 4 radians. And there's a small angle approximation in here with the theta, so we have to remember that we are working in radians. So if we convert this down, this means that we can see 0.007 degrees. That's the minimum, the absolute minimum angle that we could see a difference between for our eye, if we're looking at the Rayleigh criteria. However, when we actually start looking at what the eye can see, most situations where we have corrective lenses or naturally occurring perfect vision, 20/20 vision, the angle that we can see is 5 times 10 to the minus 4. So not 1.2, but 5, which isn't that much. We can see it says 0.029. So it's only about 4 times larger the angle that our eye can see than what the absolute limit is for our eye, which is just kind of remarkable that our eye can see that accurately with how all of our bodies are made, and just, different people have different eyes and all that stuff. So the absolute optical limit is only about 4 times better than what we actually can see. Well, what does this mean? Well, it means that if we're looking at 2 people walking side by side, say 2 feet apart, and they're walking towards you, maybe a significant other and your worst enemy, you cannot tell the difference between your significant other and your worst enemy at 4,000 feet if they're walking 2 feet apart. You just can't do it. Optically, with this resolution, we can't figure it out. And this is just nothing more than geometry, looking at this triangle. If we actually wanted to determine if your significant other is your significant other, it's actually going to take them even closer. You have to be about 600 feet before you can actually start to see the resolution between the two. If you actually look at, don't fire until you see the whites of their eyes, that's really close, So to be able to see the distance between your iris and actually just inside your eye, which is only about 1 centimeter, you have to be even closer than that. So this is kind of a cool little thing that happens, and it not only happens for our eye, obviously, but it happens for other things such as telescopes, microscopes. We have this image that we can see, and we are limited definitely by the resolution of our eyes for this case.